All right. So we can start. So last time we talked about uh unsupervised learning, and the problem that we were looking at was data clustering, and we learned multiple methods. We learned k-mean clustering. We also learned DB scan. So that is one spectrum of unsupervised learning. Today, we will look at another spectrum of unsupervised learning, which is dimensionality reduction. We actually use this a little bit at the end of the last class when we want to visualize our cluster, right? Because um, the canvas, the graph that we can draw is in 2D, and our data is in high dimensional. So we have to reduce the dimension into 2 dimension before we can actually present them in a graph format. So today we are going to look at that step in more detail. How are they computed? What are the main methods to use, right? Because last time we used PCA, but there are many more methods that we can learn. So the outline for today, we're going to go back a little bit to the unsupervised learning to show you all of the spectrum of the different type of supervised learning. And then we will go down for dimensionality reduction. And we will have 4 methods that we are going to learn today. So we actually used PCA last time. There also LDA. We have t-SNE and UMAP. And these 4 methods are going to be your go-to. Basically, like a lot of people use them, and it will be your first choice for your research if you decide to reduce the dimension of your data. So looking back at unsupervised learning, the tasks, we want to find fx, like we want to find function x that map x into output y. And the challenge of unsupervised learning, because there is no ground truth, so your answer, right, your function f and then your output y are very subjective, right? What I mean by subjective is that all of them are correct, but people tend to accept the correct answer with enough evidence. So when you are doing unsupervised learning, you actually want some meaningful result, right? You want some meaningful result. And so there are methods like neural network and deep learning, and those methods actually are very hard to interpret, right? It's hard to explain the answer. And so for unsupervised learning, people tend to use mathematical, right? So for us, so we haven't done any, smart method. Smart method, I mean like to train the model or like to use like neural network, because for unsupervised learning is basically you need to be able to explain your result, because there's no ground truth. Anything is correct, but whether or not your result can be useful in some applications, that is up to your interpretation. So last time we learned about data clustering, and our output would be just the class, like the cluster number. Each x will be assigned into one of the cluster, like from 1 to k, and you can use the information for each cluster to actually group your data. And what you do with the group is totally up to you. Like if you do customer analysis, right? You can group your customer into small group, and then you can decide to do experiment or maybe show some advertisement to some of those customers differently based on the group. Today, we are going to learn about dimensionality reduction. And this doesn't give you the output. There's no output per se. There's no Y. What we have is we have our data at maybe like M dimension, right? There are M columns in our data. And the output that we want is a smaller X, right? We actually want X, it should be an X palm or something, right? To denote that it's different X from the input. And the output that we get, the dimension would be less than the one that we start with. And there are many benefits of having a small dimension, right? So the first thing that comes to mind would be like computational time, because like if you have, let's say, like 2000 features, you have to like do the calculation 2000 times, but if you have like only 100, then you would do 100 times. So having less dimension can sometimes lead to a good performance. And today we will look at some of the methods that can reduce dimension. And each of the method actually work in a different way. So it's not like all the methods solve the same problem, because dimensionality reduction can have different purpose, and each purpose you use different method to solve. So in general, dimension would refer to the number of features, right? The number of columns in your data set. And when you have more dimension, what happens is the point are far apart, right? The point are far apart because the distance is actually accumulated across all of the dimension, right? If you look at the Euclidean method, because I'm writing with my mouse, I don't actually have my tablet with me, so wait, bear with me. So in the Euclidean, right? So you have like the square root of each of the dimension, right? Delta x plus delta x2 square, and then so on. So the more dimension you have, the more distant you have. And that makes the space very sparse. And when you have a very sparse data set, it's actually very hard to come with a pattern, because everything is so far apart that you are not really sure these 2 points can relate to each other. And so some of the dimension may not be relevant, right? May not be relevant to what you are trying to do. Like maybe there's some noise, or maybe it's not that important, but it's still part of your equation. So it should take up more computational power, but it doesn't contribute to any meaning you get at the end. The direct application for dimensional reduction, as you will see today, is mostly visualization. And the visualization is the key part, because we want to understand, right? So we want to look at a whole picture of our data set, but in more data set, they have more than 2, right? They have like maybe 1,000, and to visualize them, you need a very good dimensional reduction technique, because when you reduce dimension, you lose some information, of course, but the information you lose should be very, very small. So you can see that there is an objective that we want, is we want to reduce dimension without losing too much information, right? So that is our like objective function, but it's not written in mathematical form yet. So we still have to come up with the formula. Another application is noise reduction. Now, in noise reduction, we want to single out some points that are actually not very good, and some of the technique can actually detect the noise in the dataset. So it's not just the technique for just reduce dimension, but the byproduct of that can reduce the noise as well, right? So noise here can have two meanings. The first meaning is just a noise data point. Another meaning is the noise on the feature, meaning that the feature that's not important, it actually becomes noise in your calculation. And then the last one would be feature engineering. So the technique for feature engineering is you take the data set and then you want to pick out, right? You want to maybe convert your raw data into a meaningful feature that you can explain, and the meaningful feature will lead to like a future application. Like for example, if you want to do the classification and you want to reduce the dimension first before you perform like classification, so you can have like a better performance. So that are some of the main applications for dimensionality reduction. So within dimensionality reduction techniques, there are two main categories for this. The first one is called feature selection. So feature selection, as the name suggests, we actually select a subset of feature, or you remove irrelevant or redundant. There are techniques like you can find correlation between each column, and then you can remove the column that have low correlation or maybe high correlation, right? Because sometimes if two columns have high correlation with each other, you can actually infer one column from the other. So it's better to just include one and not worry about another one. They also call it wrapper technique. So the wrapper technique, like repeatedly remove. So there is the calculation for the column correlation, and you want to remove column that reduce that score by a little bit, and then you repeat you repeatedly remove column until you left with a strong set of features. There is also embedding technique. I will not cover them in detail. I think there is a class like feature engineering that you would learn all of this in that class. In our class, we are interested in feature extraction. So feature extraction is not just picking out the column, but you want to transform the entire data into new lower dimensional space. So you have your data in one space, and then you want to transfer them into a lower space. And this can have two benefits. The first is you can actually apply this in many data set because the method is actually very general, very generalized. So you can apply this onto many data sets. But for feature selection, you actually need some background information on the data, so you can pick the feature better. So we will learn 4 methods, and the main example would be PCA and t-SNE. Okay, so far so good. Any question before we actually go down into the dimensional reduction techniques? So if you have any question, maybe during the lecture, feel free to speak up, or you can write your question in the chat. Because in online, I cannot see your face, so I'm not sure if you actually follow or maybe you are still not sure. So yeah, if you have any question or you do not follow some of the logic, you can write in the chat. Okay, so let's move on to the next part. So the first technique that we are going to learn today is called principal component analysis. And this is the most common method for dimensionality reduction. So when people want to reduce dimension, they would try this one first. So what is PCA, right? So the PCA is transforming the data into new coordinate system. And when you transform the data into new space, you need to have some constraint or some objective that you want to achieve. And the way that PCA does is it actually generates the new coordinate system, basically the new axis of your data. So normally, let's say when you have 2-dimensional data, you have like X and Y, right? You have X is the horizontal and Y is like the vertical. And for PCA, they actually want to find a new axis, right? So in this picture, you have the C-axis and then the W-axis. And once you have this new axis, you actually project, you transform the coordinate of the O point into the new system. And the way that PCA choose the axis, right? They choose the axis that had maximum variance. So basically, there can be many axes, but they will choose the one that maximize the variance. So what is the variance, right? Basically, the spread of data. They want to pick the axis that the data spread out the most. That is your first principal component, or the first axis. And then the next axis would be the one that are perpendicular to the first, and then you repeat the same process, right? If you want the second dimension, you have your first dimension, you look at all of the axes that are perpendicular to the first, and then you pick the one that have the next maximum variance, right? So each of the axes that you add is going to have a lower variance, but it will be in the decreasing, right? So you pick the maximum variance first, and then you go down the list. And the goal is to reduce the dimension while retaining the most important information. So if they have a high variance, it means that it actually contains a lot of information because the data is far apart. So you kind of want to keep that same structure, right? That the data is far apart when you map the data into the new coordinate system. So how can we do that? The PCA have 5 steps. There is a library that will do all 5 steps for you, but it's important that you understand what each step in the PCA does. And later on, when we go to do the code in Colab, I will show you both way. Show you how to do it using the package, the library package, and if you want to do it by hand, actually we simple to do it by hand because we actually have linear algebra library that you can also use. So PCA is rely on linear algebra. So hopefully you review your linear algebra knowledge. So the first step in the PCA, you want to standardize the data. It's basically scaling. And we learned last time, right? Before we do clustering, we want to scale because the range, right? The range of each dimension affect the performance of the clustering algorithm. So in PCA, if you want to find the variance, right? You want to find the variance that when the data for each feature should have zero mean and a unit variance. So you want to make all of the dimension to have like similar probabilistic distribution, right? Here we actually use the standard distribution. So for each data, we subtract the mean, and then you divide it by the sigma, which is the standard deviation. So you do this for every column. So you do each column separately. You calculate the mean of each column, and then you subtract x with mean, and then you divide it by standard deviation. So this is the first step, right? You want to scale the data first, and this actually help when you perform linear algebra because a lot of linear algebra algorithms actually require the metrics to be, in a certain form or exhibit some properties like semi-definite matrix or the symmetry matrix and so on. And so standardize the data actually help with that aspect. So this is the first step. Just subtract the mean and divide by standard deviation. Now the next part, I want to compute covariant matrix. Basically, the covariant matrix is a matrix of a correlation between every pair of point, right? Every pair of point, and it's going to measure how features vary together. So you will see here is the data, right? And then you do the C transpose C. So you have endpoint, right? You have endpoint. So you end up with n square covariant matrix. And in this covariant matrix, basically it's going to tell you what are the variant. So in the diagonal, right, you have the variant of just one variable, and then you have a joint covariance between two data points in the other spot. And this will tell us how each feature can affect each other. But we are not done with the covariant matrix. So the metric is just we calculate some measurement, right? We get some probabilistic distribution data from the data. And once we have the covariant matrix, we are going to find the eigenvector and eigenvalue, right? So we want to solve the eigenvalue problem. And the eigenvalue problem is of the form, right? So we have matrix C, right? We have matrix C. We want to find the eigenvector and eigenvalue. And these two will determine our axis, right? The eigenvector is going to be our new axis, right? Our new axis. So to solve the eigenvalue problem, we set up the equation to be c times v. So we have some vector equal to lambda v, right? Lambda v, and this lambda is our eigenvalue, and v would be the eigenvector. So we want to solve for both, right? We want to know both lambda and v. So for this equation, they actually have many solutions. So one matrix can have many eigenvalues and many eigenvectors, and there are many ways to solve them. I'm not going to go into detail how to solve the eigenvalue, but if you were to do it by hand, maybe you have a 2x2 matrix or 3x3 matrix, you can actually transform this equation, right, into like CV minus lambda V equal to 0. And then you have C minus I lambda times V equal to 0. Right, so basically you move lambda V into the left side, and then you make it a matrix. And then you can solve the left side because V is not 0, right? We don't want eigenvector to be 0. So the only thing that can be 0 would be this matrix. So if you can solve this matrix equal to 0, right? So if this matrix equal to 0, then you can get all of the eigenvalue. And for each eigenvalue, you put it back, and then you can back solve the eigenvector afterward. So let's try. I will give you a few minutes to find the eigenvalues, just the eigenvalue of the following matrix. So I have two matrices, 5412 and 311, 242, 113. So let's see if you can find the eigenvalue of this matrix. If you get the answer, you can type your answer in the chat. Any answer for the first one? The first one should be Very easy because it's only 2 by 2. Right, so you want C minus lambda I equal to 0. Right, so you have 5, 4, 1, 2, and then you minus. Basically, you have lambda on the diagonal, right? And then you set it equal to 0. So in the first equation, you have 5, 5, right? So you have 5 minus lambda, right? 5 minus lambda, and then you have 4, and then you have 1 over here, and then you have 2 minus lambda. Right, and then you want to set it to 0. Right, and then when you get to here, oh, even though I said like equal to 0, but what actually happened is like you want the determinant of this to be equal to 0. Now you want the determinant of this matrix. So what is the determinant? Basically, you multiply the diagonal and then you minus them. So you have 5 minus lambda times 2 minus lambda, and then you minus 4, right? And then you set it equal to 0. And then in this equation, you get then you get 6, right? So 5 times 2 is 10, but minus 4 is 6. And then you have minus 7 lambda. And then you have plus lambda squared. And then you set it equal to 0, right? And then you have the lambda to be is either 1 or 6, right? 1 or 6. So that is the 2 lambda, right? So the trick here is just to actually calculate the determinant of the C minus lambda I, and then you set this equation equal to 0, and then you get your lambda. If you want to back solve the vector, right? So you can say 5, 4, 1, 2 times, I don't know, v1, v2, right? And it have to be equal to, let's say I want to find the vector for lambda equal to 1. So this would be equal to 1 and then v2, right? Because the coefficient would be 1. And then when you solve this, right, you would have like 5v1 plus 4v2 equal to v1, and then 1v1 to v2 equal to v2, right? So you have two equations, you have two variables, you should be able to solve for v1 and v2. And then you do again for lambda equal to 6, then you get a different v1 and v2. So that's how we find eigenvalue and eigenvector from the matrix. And once we have the eigenvalue or eigenvector, we can start transforming our data. So the principal component, right? The principal component, we actually pick the top k eigenvector, right? So all of these lambda that we find here, right? We're gonna have many lambda. We actually sort the lambda by its absolute value, right? We sort the lambda by absolute value, and then we pick the top k. So you have, so normally, the number of eigenvalue would be like the same number of the column, but you want to reduce dimension, so you pick some subset, right? So in the equation, right, you have the C of each of the V, and then you have all the lambda here, right? And you want to pick just some column, right? You want to pick some column. Basically, you pick from left to right if you sort your eigenvalue from largest to smallest. And each of these vector, each of these eigenvector would be your new axis. And then you can do the dot product. Basically, you multiply, you left multiply, right? So you have a lot of lambda here, you have a lot of eigenvector here. You pick the first k. Basically, you pick the first column, the first k column. Right? If you sort the lambda by its absolute value, right? So lambda 1 would be the highest magnitude, right? And then you take the k, and then you get this vk. So the vk would be basically your projection matrix. So you have your projection matrix, and you write multiply your data with the projection matrix, and then you will get your new data. And this new data will have k dimension. So that is how the PCA transform the data into a lower dimension. So it calculates the volume matrix, it finds the eigenvectors, eigenvalues, and then you select the principal component, basically your destination dimension, how you want the data to be, and then you project onto the lower dimensional space. And the beauty of being eigenvector is that each vector that you get, like each vector that you get, are actually perpendicular to each other. So the eigenvector actually form a new coordinate system. But we don't take a full coordinate system, we only take the top k. And because we believe that the data, the axis that have the high eigenvalue should have high information. And the dimension that have lower eigenvalue contain less information. So we throw away the less information axis, And this way we keep the highest possible information when we project our data into lower dimensional space. Okay, so far so good. So if we want to like so we have this like three feature, and then we have key data set, and we want to project this into 2D space, right? Basically we have to follow uh, the procedure, right? So for each column, you have to transform it by subtracting mean. So you have like 3 minus the mean of 1, 2, 3 is 2, and the standard deviation, I think it is like 1 square divided by n minus 1. So this should have 1, right? Should have 1 SD, right? And then you do this the same with everything in the column. So you standardize this one first, right? So once you get C, then you can find eigenvalue, eigenvector. Oh, you have to do this one first, right? 1 over n minus 1. So in this case, n is 3. So it's 1/2, right? So it's 1/2. And then you do the C transpose times C, right? And then you find the eigenvector and eigenvalue. So to do it by hand, it actually really difficult because there are a lot of calculation, like for each step, like you'd have to do multiplication, and then you have to solve for eigenvalue. So the method that I show you is actually the straightforward way of doing PCA. There are a shortcut per se, like not really a shortcut, but they are numerical method, right? If you take numerical method, they are a way to approximate all of this process, because each process is very time consuming, because when you multiply all of the data, right? If you have n data, you have to do n square multiplication, and that actually very costly. So there are many ways to actually skip this part and then find the eigenvalue straight from the data. But we'll not cover that here, but you will learn about it if you take numerical method or numerical analysis class in mathematics. For us, all those methods are actually implemented already. So someone kindly write the code for us, so we don't have to do heavy math. But it's just that we have to understand that if you were to do it by hand, this is how you do it. But if you want to do it by computer, there is another way of doing it. So in some of the text you read in the book, the method may not be exactly as I describe here, because some of the method use numerical method, which is an approximation algorithm to compute the eigenvalue or eigenvector, and that is faster for a computer, but it's actually harder to explain in like 5 minutes. So this is how we do PCA, right? So standardized data, compute variant, find eigenvectors, select principal component, and then project the data into lower dimensional space. Okay, any questions so far? I think most of you use PCA at some point, right? At least for visualization. right? When you want to plot the graph or something. Okay, go ahead. You have question. Some ML use min-max, some ML use standard scalar. So what kind of situation we want to use scaling method? So the min-max scaling and standardized scaling, it actually based on the math problems that you want to do afterward. Now, in clustering, right? In clustering, you want the data to have the same range because you want to treat each dimension equally. That's why we use min-max scaling. But PCA, right? PCA, we don't want to confine each. So we don't treat all of the column equally, right? Because we have, like, our opinion is that some column contain more information than the other. That's why we pick the principal component. And so we don't use min-max scaling here, but we use standardized scaling. And the standardized scaling that we use, basically we make sure that the mean is 0, and then the standard deviation would be 1. So even then, we still have like even though we try to make the standard deviation to 1 of the dimension, some of them are spread out, some of them are condensed into the average. And so the data, the dimension with high variance, even though we try to squeeze it with the standard scaling, that should contain more information. So for PCA, we would use standard scaling because we want to compare the variance, right? We want to compare the variance for each dimension. And min-max scaling does not allow us to compare because it's just mapping everything into the smaller space, but the standard scaling is something different. So the choice of scaling will based on the math problem you do afterward. And you will slowly learn that each ML we learn, we are going to use different scaling. So right now we know that we use min-max for clustering, and we know that we use standard scaling for PCA. But for the method, maybe we use something else. So does this answer your question? Okay. Any more questions before we move on to the next technique? All right. So we're going to move on to linear discriminant analysis. So PCA is actually good in general. And in PCA, you don't assume anything about the data. Basically, you have the data, and then there's no outside information about the data. And that is the best you can do, right? You perform PCA to reduce dimension. Now, in linear discriminant analysis, we actually know something about the data. So LDA is a supervised method, right? So now it's becoming a little bit crossover, right? So we think of dimensionality reduction as part of unsupervised learning. But now you have a method that acts as the supervised learning. So the data must already be clustered. So what it means is that in your data set, maybe you already have category. You already have category data. And when you have category data, you cannot use that in PCA directly, right? In PCA, you only care about numeric data. So all the columns that you map into a lower space have to be numeric. So if you have category data in your category feature in your data, you have to remove it before you perform PCA, right? Otherwise, it's gonna mess up really badly. So now in the LDA, if you have category data, you can use that. And the way that we use the category, we use it as a cluster, right? So our data now have cluster, basically the category in the dataset. And this method LDA, it maximizes the class separability, right? So what it means is that if the data belong to different class or different cluster, when you map onto a lower dimensional space, that data should be far apart because they come from different clusters, right? So they're going to use the class label to create a discriminant axis. So there's no covariant, no eigenvector, no eigenvalue. It's going to use the similarity measurement to decide which axis we want to project our data on. So for example, right, we have this column data, right? We have red and then we have blue. So we know that our data have two classes. And if we are to perform PCA, right? If you want to perform PCA, it's gonna, let's say like this is your first axis, right? Because this direction have the highest variance. And so all of the points are projected onto the axis, right? And then when you do the projection, you can see that data from two classes are actually mixed up, right? In the mix up. And you already see this when we perform the clustering last time, right? We perform clustering, right, in the last class. And then when you do the plot, you can see the point like are overlapping, right? Different class overlapping on each other. So that is why if you know the class in S1, for better presentation, when you map it onto a lower space, they should be far apart, right? They should be separable. So in the LDA, they should be click this axis instead. And then when you project the point onto this space, you can actually see the separation between two classes. So this is how LDA works, right? So there's no eigenvalue, eigenvectors. They just want to find the axis so that when you project it, the data from the same class are clustered, and the data from different class should be far apart. And in the LDA, we have two measurements. We have SW. This is called a similarity score. For W will be the within class. So it's gonna measure basically the distance, right? So this one is the distance between the average, right? Between the average of the cluster, right? So mu I belong to the CI. So mu I is like different to when you run k-mean. So it's a representation of the cluster. So for each cluster, you compare the average vector, right? And then you calculate the distance. and then you sum up. So basically, is the sum of every pair of points within the same cluster, right? So basically, every pair of red point, right? You draw every pair, you calculate the distance, and then you sum it up. So that is your similarity score within the class. For SB, you look at between class, right? Now, in between class, like you look at different class, and you're not going to do the every pair of the point from each different class because it's really messy. So what you do is you look at the representative of each class, right? So mu I is the average vector of cluster I. And this mu is the average of the average. Basically, it's the average of the entire data set. And this is, you calculate the distance from the global average from the local average, right? The local average. And for us, right, we want SW to be small, right? You want the distance between the class to be small. And you want the distance between class to be high. So when we combine the two score, right, we have SB, we have SW, we put SB on the top, we put the SW on the bottom. So, and then our W here is our data in lower dimensional space. So we learn the data directly, right? So this is the function, right? So this is the objective function, right? We want to learn the data directly. So in PCA, all the process that we did is to find a projection matrix, right? And then you multiply that projection matrix into our original data to get the new data in lower space, right? In LDA, you don't do that. You actually have your new data as a parameter, right? You put your new data in the parameter, and you combine, like you have the score, and then you multiply like this. There's like the mathematical explanation, but I'm not going to go into detail. But this is how they frame the equation. So W here is the data in lower dimension. X is the data in high dimension or in the original dimension. And basically, you want the top to be high, right? You want the bottom to be low. So basically, you want to maximize this function, right? So it's become a maximization method. Okay, let's look at the step in detail. So the first thing first, right? We compute the scatter matrix, right? The scatter matrix, and the scatter matrix, right? We have to calculate this, right? So we calculate the mean vector of each class, like basically for each CI, we calculate the average. And we compute the overall mean. So basically you sum X and then you divide it by N, the number of data. And then you compute the scatter matrix. And the scatter matrix, basically you compute the score, right? SW and SB. Right. So these are the metrics. Right? Because when you do the metric here, right? You have your data point, right? And then you time, like this is the transport. So what you get is you get the matrix, right? So you have SW, SB. Like both of these are called scatter matrix. Right. So basically each spot is going to be a pair point. Right. Because this is the vector, and then this one, like when you transport it, you get the horizontal, and when you multiply vertical with horizontal, you get a full matrix. Right. So SW and SB are M by M matrix, right? Basically the number of dimension. And then, well, we actually still have to solve the eigenvalues. So basically, our covariant matrix that we get from last time, like from the PCA, we actually use the scatter matrix instead, right? And then you again project it onto the lower space. So when I say that, like, we actually want to maximize this expression, it leaves LDA with a room to choose, right? So you can maximize this using auto method. But doing the eigenvalue problem is one of the solution to get this expression as high as possible, right? So you have the inverse of the scatter matrix within the class times scatter matrix between class, right? And then you want to find the eigenvector. And the process would be the same as the PCA, right? When you pick the top k eigenvector, you have the eigenvector matrix, basically the projection matrix, and then you multiply the x, and then you get dy. So the difference between PCA and LCA is that even though both of them solve the eigenvalue problem, in PCA we do standard scalar, right? We do standard scaling, but in LCA, as you can see, we don't do the scaling. And the reason that we don't do scaling because here we cannot scale when we compute the scatter matrix. So the scatter matrix already did some kind of scaling by subtracting the mean. And therefore, in LCA, you don't do scaling at all. Right? In PCA, you still have to do scaling and then do the PCA. But for LCA, you don't because the scaling is already part of the algorithm, right? So that is the one of the main difference. So as you can see, right, there are times that you do min-max scaling, sometimes you do standard scaling, or sometimes you don't do it at all. So it depends on how you understand the method, right? So if you only know, like on the left picture, right, you only know just a general information, then you are not sure whether or not you want to use scaling or not. But if you understand the algorithm and the algorithm doesn't do the scaling inside, then you have to do scaling by yourself. But if the algorithm already did the scaling for you, then you don't use the scaling. So that's why it's important for each method that you learn the mathematical formula. Because the choice of the scaling based on the math problem that you are going to do later on. So in LDA, you don't use any scaling. Okay. So what are the applications that they use for LDA? They use this as a facial recognition. So you have a face database, right? And then you split into train and test. Right? You split train and test. And you kind of want to do classification. Now, in classification, right, you want to build a classifier, right? So in the classifier, we actually need a feature vector, right? A feature vector. And you can use LDA to compute the feature vector because here, right, in the LDA, it actually map the input into a new space, right? A lower dimensional space. And when you map onto the lower dimensional space, you actually make sure that the data that are in the same person, basically the face of the same person, are actually mapped into a cluster, right? A closer cluster. And the face of someone else should be far away, right? So in LDA, so in a typical classification, right? You have your target, right? You have your target, and then you have your feature, and you create a model, right? A machine learning model to get a feature to the machine learning model onto the target, right? And then the machine learning will learn the weight, and then you multiply weight into the feature, right? And then you get the target at the end, right? So that is the typical machine learning for classification. In here, you can actually use LDA as a feature extraction. So instead of getting the feature and then do the classifier, right? We don't have to do any learning at all. The classifier can just be Euclidean distance. So basically, when you have a test image, right, you map it, when you have a test image, you map it onto the same space, and then you just compute the Euclidean distance, right? If it's closer to whose face, then you can assign that face. So basically, it becomes like nearest neighbor algorithm as a classification, right? So there are many applications that LDA can fit within the realm of a supervised learning, right? So this is very interesting because when you do a typical machine learning for facial facial recognition, you basically have to normalize your face, right? You have to normalize the data, like for each of the image, right? You normalize so that the average pixel value should be 0, and then the variance should be 1 before you actually do the feature extraction or to use machine learning to learn. But for LDA, you don't have to do the scaling because it's part of the algorithm, and then you can get the feature vector directly. And your classifier can just be nearest neighbor, right? Very simple classifier because you actually did a lot of analysis in the LDA. Right. So there are many ways of solving the same problem. It's just how you picture it, right? How you imagine what would be the application. Right? So by design, the feature should maximize the class separation already. So any classifier should perform well. So you don't actually need like deep neural network. Okay, so far so good for the LDA. So LDA is a mix of like unsupervised and supervised, right? So you can use target as the input for the dimensionality reduction, right? But I mean, instead of think of it as a dimensionality reduction, you can think of it as a feature extraction. So there are many ways to think about it, right? When you map something from original space into a lower space, you get some feature. But of course, for LDA, the feature doesn't actually have meaning. Like most of the time, it's going to be some mathematical, like abstract space that only computer understands. Sometimes humans can actually try to crack, right? Try to crack the all of the axis, like what does this axis mean? But most of the time they don't. That typically don't. Okay. So let's move on to the nonlinear dimensionality reduction. So what we have done so far is a linear, right? So what do you think is linear? Because everything that when you do with metrics, right? When you do metric multiplication and so on and so forth, like solving a set of equations that are linear, right? Your equation is linear. So the solving part is actually really simple. And when the data has a nonlinear pattern, right? So what I mean by nonlinear pattern, right? If you remember, let's say my data, right? Two group, like the group is the outer ring, and another group is the inner ring, right? So this relationship is not linear, right? Because it's kind of like a ring, right? It's a circular. So the pattern that we want to learn, sometimes it's not linear. And if you can detect, or if you think, like if your instinct tell you that, oh, the pattern should be nonlinear, then you would not want to use PCA or LDA, right? Now the example would be like gene expression, right? Gene expression, because it's like protein folding, basically like your DNA. And the DNA doesn't actually have the linear pattern because of the 3D structure. Some of the image processing technique, you cannot use PCA. But we did use LDA, right, for facial recognition, but there are other processing technique that prefer not to use PCA, LDA. We have a customer segmentation. Basically, you just try to cluster your customer, and the customer behavior is typically not linear. And we're going to learn two techniques in this class, t-SNE map. For t-SNE, it's going to preserve pairwise similarity in a lower dimensional space. So one of the method is fully unsupervised, no target, no category, just number, just numeric feature. And t-SNE, when you project the data into a lower dimension, right? For example, if I have A, B, C right here, right? A, B, C, and then C is far away. So when I map this into a lower dimensional space, the distance from A to B should also be less than from B to C, right? And less than is does not set just regular less than, but it also have to be like proportion, right? If it's like 3 times longer, then when you project to lower space, then it should be roughly 3 times longer. So that is how t-SNE try to do, right? It try to preserve pairwise similarity. If the 2 points are close to each other in the original space, it should be close in the reduced space. For UMAP learn lower dimensional representation while maintaining local and global structure. So it's more general than t-SNE. Basically, it look at the data as a big picture. If the data is already clustered in high dimension, you want to preserve kind of that cluster. You don't want the cluster to be separate, right? You don't want it to be separate from each other. So you want to map the same cluster onto the lower space. And for the global structure, right, when you have many clusters, you want to make sure that each cluster are still separable when it mapped into a lower dimension. So let's start with t-SNE. So the t-SNE, the full name is the tree-distributed stochastic neighbor embedding. So it's an embedding method. I will fix this one later, but it's actually just the Gaussian kernel. So in t-SNE, we define pairwise similarity, right? So Pij here is the probability that xi and xj are similar. And the way that you do it, you basically you look at the top one, right? You look at the top one. You basically find the distance from xi and xj, and then you plug in the Gaussian kernel, right? So it's the e to the minus delta x divided by 2 sigma square. So that is the Gaussian distribution, right? The equation for Gaussian distribution. And that will be your similarity score, right? Don't worry about the bottom one. The bottom one is just the scaling factor so that the probability is sum to 1, right? That is what it does. So you only have to understand the top part, right? The top part is just the normalization term to make sure that the probability is all sum to 1 and so on and so forth. So you only need to understand the top part, like which is the one that will determine what is the score for INJ. So if the data is close in here, right? When you map onto the lower space, right? You want it to be close to each other. So basically, you kind of like create like a ring, right? A Gaussian ring, a Gaussian bell curve, but in high dimension, right? And the further apart, then when you map into the lower space, it should actually be further apart, right? So you look at this in like in a Gaussian way, in a normal distribution way of calculation. So we start with giving the score, right? Giving the score, and when we go into a lower dimension, right? So this xi here is actually the data in the original dimension, okay? And yi is the data in lower dimension. That is what we want. We want yi, right? We want to reduce the number of dimension. And we also need to define the pairwise similarity in the lower dimension. So when we define the similarity, we kind of do the same way, right? So here we compute the probability that 2 points are the same, right? And then you divide it by the normalization. Here is similar. So the top part would be like the probability that yi and yj are the same. But we actually use different distribution function. And this function here, right, is called t-distribution. Right? Basically, you just you subtract, right? You subtract the value, you compute the magnitude, like square, and then you plus 1, and then you do the 1 over. And the reason that we do it differently, like for high dimension, we use Gaussian. But for here, we can just use t-distribution. And the reason is that in high dimension, the data are far apart. So because the data is far apart, you can have the bandwidth, right? You can control how far it can be, right? By like if you pick the bandwidth to be high, it means that your Gaussian distribution will be, will be more flat, right? So you can control the flatness with the sigma. So in high dimensional space, you don't know how high they are, but you can pick the bandwidth that correspond to the sparseness of your data. In the lower dimension, the data is now closer to each other, right? So we don't need to use Gaussian distribution anymore, right? Because we don't want to introduce another parameter. And t-distribution has no parameter. So that's why we pick t-distribution. So we pick from the top, right? Your t-distribution, and the bottom one would still be the normalized, so that the sum would be like equal to 1. So don't worry about the bottom part. And these three distribution that we have, it actually bell curve. It's still a Gaussian, but the tail is heavier. And then we don't have to deal with additional parameter. So that's why in these algorithms for t-SNE, we only have one parameter, which is the bandwidth of the Gaussian kernel. And it will depend on the size of the data, right? If your data is high or your dimension is high, then you might want to increase the bandwidth. But if your data is like closer to each other, you can reduce the bandwidth. But in lower dimension, you don't actually need to control much. And so we have two scoring, right? We have pairwise similarity in original dimension. And then we have the pairwise similarity in the lower dimension. Now the difference is that for Pij, we can calculate it because we know xi is our data, we know xi. But for Q, right, for Q, we don't actually know yi, because yi is what we want to learn, right? We want to learn yi. So we want to pick yi, basically. But we cannot just pick just yi randomly. We want to pick yi such that pij and qij are very close to each other statistically, right? If pij for this pair ij is high, you want qij for the same pair to be high as well, right? So basically you have two distribution and you want two distribution to match in structure. And to do that, we have to use Hilbert-Leibler divergence between P and Q, right? So we have this formula, right? The sum of the Pij log Pi divided by Qij. And it's basically, it's measure how two distribution are similar to each other or not. And the lower the value, right? If Pij and Qij are the same, you get log 1, right? You get log of 1. And when you get log of 1, the entire thing is 0, right? Because log 1 equal to 0. And everything is equal to 0, it means that P and Q are the same distribution. And that is our goal. We want this to be as close to 0 as possible. So we want it to minimize, right? We want to minimize this cover the KL divergence between P and Q. And to do that, you can use gradient descent with respect to yi, and it's often the choice for the optimization method. So for t-SNE, right? We don't do eigenvalue, eigenvector because that are linear. Those are linear, right? But for nonlinear, we use KL, right? Hilbert-Leibler divergence. And then we use gradient descent to find the lowest value of this expression. So there are other choice of optimization, but because when we compute the Pij and Qij, everything kind of come back to being linear, right? Pij and Qij is not actually nonlinear, so gradient descent would work most of the time. But there are other optimization methods that you can use. I'm not sure if you are familiar with gradient descent. Have you heard of gradient descent? You probably learned it in optimization class. Yeah. So you have heard of it. Yeah. So it's similar to Newton method. It's another name, Newton method. Hopefully you still familiar, right? So basically, when you have like a function, right, and then when you are over here, you calculate the gradient, right? You calculate the gradient, and then you update your solution with the smaller gradient, right? So that is the T-distributed stochastic. So it's an optimization algorithm to find the data in lower dimension. So for here, there's no projection. You don't project anything, but you actually construct like a low dimension, right? A low dimension. So compared to PCA LDA, this work on just one data set, right? If you have a new data, right? If you have a new data come in and you want to reduce the dimension of this data, you have to do the entire process again. Right? You have to do the entire process again. But for PCA and LDA, you have your projection metrics, right? So you can keep your projection metric. When you have new data, you can just multiply the projection metric to the new data to get the lower dimensional version, right? So for the linear, it's actually convenient for the new data that come in, and you want it to project into the same space. But for here, for the nonlinear method, because it uses some sophisticated algorithm, some distribution. So when the new data come in, you have to do everything again. So it's slow for the nonlinear. So basically, you want to do it on the data set that you don't expect to expand. Right? So this is the t distribution. So you calculate this, basically is constant because your data will never change. And then you set up the queue, and then you do the optimization. So that is the high level. I'm not going to do detail how to compute the gradient with respect to the yi for this expression. Basically, you just plug in this equation, and then you just look at which term is constant with respect to yi, which term is not, and then you do the gradient, like you do the derivative. So that for the t-SNE. Now the last method for today is uniform manifold approximation and projection. And this algorithm is a graph-based algorithm. And what they did is that for each data point, it is a vertex in the graph. Right? So we have a graph in computer science. So it's not the graph that we plot. The graph in computer science, we have vertex and then edge. Right? And then the vertex contains some information, the edge also contains some information. And then we have like a series of algorithms that are based on graph. So everyone know, right? Graph in computer science, hopefully. So each data is a vertex, and then the k nearest neighbor will form an edge, right? So you have your data, you look at your neighborhood, right? And then you pick the k nearest neighbor, right? So you have your data, right? And then you look at the neighborhood, right? And then you pick your k nearest neighbor, and then you form an edge between them. Right? You form an edge in between with your neighbor, and then you assign the weight for an edge. Now, the weight basically is a measurement how close they are, right? Basically, is a similarity between two points. And you can use, maybe you can use Gaussian kernel, or you can use Laplace kernel for the weight. Is your choice. So for Gaussian, you have one parameter. For Laplacian kernel, you have two parameters. And basically, you want to try as many kernel as you can, because for UMAP, there is no like analysis way to pick like, okay, this data use Gaussian, this data use Laplace. There's no correlation. So in most cases, when you are performing UMAP, you will use like different version of UMAP. Right? You pick the Gaussian kernel, you pick the Laplacian kernel, you pick like other kernel, and then you compare the result, and then you pick the best one. And because there's no like rule of thumb that, okay, in this situation you have to use Gaussian. In this situation you have to use Laplace, right? There's no such thing. So you have to try as many as you can, and then you compare the result. So that is the graph part, right? You construct a weighted graph using a high dimensional data, right? So once you have the graph, right? When you have the graph, then you want to map this graph in higher dimension to lower dimension. Basically, you want to find the embedding that preserve the structure of the graph, right? So what do you mean by the structure of the graph? The structure of the graph are like all these edges, right? So you want to make sure that when you map, right? When you map the data into lower dimension, the edge, right? The weight on the edge are similar, right? Are similar to what we have before. So you can think of this like as an extension to t-SNE, because in t-SNE you compare, almost every point, right? You compute the pairwise, but for UMAP, you only look at the k neighborhood, and because you choose k neighborhood, right? Some of the points are maybe in different, like in different cluster have like the longer weight, and you want to preserve the global and as well as a local. So the local, it would be the point that are close to each other, and then the global would be the point that are far apart. And the way that they preserve the structure is to optimize the cross entropy, right? So we have Pij, we have Wij. So the Wij is our original weight, right? Our original weight of the graph. And then the Pij is the weight in the graph in the lower dimension. And you want to optimize, right? Optimize this cross entropy so that it's going to move the point, because our point are yi, but in this equation we use Pij, right? So Pij here you can use basically the same kernel. Sometimes people use different kernel, but most of the time they use the same kernel in both high dimension and low dimension. So Pij here is actually, the Yij minus the Pi divided by sigma I. So this Yi is embedded in this P, right? So the optimization will move the point, right? We move the point closer to its neighbor in high dimension, right? Basically, you can do the gradient descent method, right? Basically, you take the derivative of this with respect to yi, and then you add the learning rate. So this one is called learning rate. It's basically a coefficient of how much you want to update your solution, right? So this is the learning rate. So you take the derivative, basically you find the gradient with respect to yi, and then you multiply by the learning rate, and then you add it to your solution. So basically, the solution will slowly move the point so that it's actually closer to the neighbor, right? Because it was closer in the original dimension. So when you map into the lower dimension, it should be still be closer. So that is how UMAP perform. There is an upgrade version of UMAP. It's called a parametric UMAP, and it's the same as the UMAP, right? But instead of doing creating a graph by hand, like basically in UMAP, each point you look at the k neighbor and then you add weight in there. But you can use neural network to reconstruct the graph, right? You reconstruct the graph from the data using neural network. And this neural network, you can do some manipulation and reduce the dimension using the similar weight, but at the last layer, right? At the last, you would reduce the dimension into the dimension that you want. So that is the parametric UMAP, right? So you can upgrade from just doing it normally and try to use neural network, right? So all these methods, right? You can actually use neural network if you can find a way to fit that in. But most of the time, people will still use the mathematical formula because it's easier to compute. Because if you use neural network, you have to learn the network too. And to learn this network, you actually have to have a lot of data. Like I think for neural network, like the minimum you would need would be like 1 million data so that the neural network can be sufficient. But if you don't have that many data, then it's just better to just use like regular mathematic formula. So if we compare each technique, right? So we have PCA, LDA. These are the linear function. And the good thing about PCA is very fast and you can interpret the result, right? Because it's the eigenvalue, eigenvector. The con would be like both of them require the linearity of the data. And most of the time it works, right? Some of the time it doesn't because if we know the pattern is linear, then you can use PCLDA. If the pattern is non-linear, then you would stay away from it. Now for LDA is focused on the class separable because it actually have the label data. Basically your column that is categorical, you can use that column as a label data. For the nonlinear algorithm, right, we have t-SNE and UMAP. For t-SNE is actually great for visualization, but the computation is very expensive, right? Because you have to optimize the KL divergence, and the KL divergence takes a long time. For the UMAP, it's a little bit faster than t-SNE because you only care about k neighbor. Right? You don't need to compute this point into every point in the data set. You only care about the close one, right? So that is why the UMAP is faster. And it's scalable because the number of edge does not like explode when you have more data because you only look at the k neighbor. But for t-SNE, you only have one parameter, right? Which is uh the the bandwidth for the Gaussian kernel, right? That is the only parameter. But for the UMAP, right, uh you have k, right? How many neighbors do you need? And you also have like additional parameter based on the kernel that you use, right? So there are more parameter that you have to fine tune, right? So you map faster, but you have to run multiple tabs with different parameters. t-SNE is slower, but you don't have to fine tune parameter that much. So the workflow, right? If you want to use this technique in your research, right? So the workflow would be you pre-process the data, then you apply dimensionality reduction, and then you train the model, right? Train the model. And in the pre-processing step, right, it also depends on your dimensionality reduction algorithm. Sometimes you don't need pre-processing, sometimes you do. This pre-processing also include like handling missing value and maybe they are outlier or something like that. So it's more than just scaling, right? There are other pre-processing method, and you will learn it in feature engineering class, right? I think we offer feature engineering class. You can take that class if you want to learn more about the pre-processing step. And for the evaluation, if you care about machine learning model more, then you would just use the model performance, like accuracy, uh, recall, precision, confusion matrix, and all of that, right? MSNE, mean square error. If you care more about the dimensionality reduction, there is a reconstruction error. Basically, you have your data in high dimension, right? And then you map it into the low dimension. And you need to have a way to map the low dimension back to the high dimension. So you lose some data here, right? You lose some data here. But when you reconstruct, you try to add the missing value. And the reconstruction error, basically, you compare these two, right? Can you reconstruct the original image from a feature vector, right? And that will be your dimensional reduction technique performed. Right? So this is how you would insert this technique into your workflow. So any question so far? So these are the 4 techniques that you have to understand, basically, yeah, at the end of this class. We will do some coding. We will take about 5-minute break. And when we come back at around 11, so we come back at 11, we will do some coding that use one of these methods. So come back at 11. And it's going to take like half an hour. So it's not long. So if you have the question in the meantime, you can write in chat and then I will come back and reply. Okay, we'll come back. Let's see. Okay, can you see the screen? Can you let me try something. Mouse right. Let me know if the font is like too small. I can try to increase the size because I'm not sure how it's shown in your screen. Okay, so in this lab, we're going to use the MNIST dataset. This is the dataset that like the handwritten digit. Basically, it's like 0, 1, 2, 3, 4, 5 to 9 to the digit. And the basically it's already have the label, right? You know, this image is 0, this image is 1, but we are going to try to like use clustering technique, like in conjunction with dimensionality reduction, right? And then to see if we can visualize, right? We can visualize the cluster in 2 dimensions. So let's start. I think if you open the Colab, it should give you the sample data that will show up on your Colab, like all of this sample data. And then you can just copy path, right? So path equal to, and then go to the MNIST data, train small, right? So we want to load MNIST data, right? So we can use, because it's a CSV, we can just import Panda as well as NumPy. So you can say our data equal to pd.read CSV and then path, right? And then, well, we can show the data sets. It's basically, it will show it's going to be, I mean, it's an image, right? It's an image. So each of the column is going to be like the pixel location, okay? And then I think they should have, uh, do they have, let me look at the data. I'm not sure if which column is the target. So I think the first column, so our data doesn't have header, right? Our data doesn't have header. So as you can see, like there are some, so it's black and white, basically black and white. And then the first column, that would be the target, basically the digit. So we have to make change, right? So we can say header equal to none, right? So there's no header. And actually I want to display the first image, right? I want to display the first image because it is an image. So I can just say the first the first column is the target, so I can remove the first column. So I can remove the first column and assign and make it target, right? So I can be the target should be 0, right? Be the first column, and then 1 semicolon is like the second column to the end, right? And then I convert them. And then I want to display the first image. So to display an image, I think I need plot lib. Can I plot image with PL3? Let's try. So there plt.im show, so image show, and then I can say data at 0, right, over the first data. And because the data is a row, so I kind of have to change into a square. So the size of the data is 28 by 28. So I say dot reshape here. And then I pick the color map to be gray, right? So if I run the code here, so you get the first image, right? So this should be number 6, right? This should be number 6, right? We can look at we can print the target at 0 as well. And so after we run it, right, you can see number 6 at the bottom, right? So we have our data, especially image, but the way that they put it, they just they just stick each row into one big row. So whenever you want to display image, you just say reshape, and then you specify the height and the width. Okay, so we have this number. So we have this data set. So the first thing that we want to do, let's try PCA, right? Let's try using PCA. So we want to basically plot each image, right, in 2 dimensions, and the color of the point would be the target. So we will try PCA first, right? So we're going to perform PCA on the data and plot each digit to scatter plot graph, right? So in the PCA, we have form sklearn. So from sklearn, we have the decomposition library, and we import PCA. And actually, we can import matplotlib again. Actually, if you already import it at the top, you can just skip. But for here, I just import it as completion. So here you can say so PCA equal to PCA, and then we put it at the number of components equal to 2, right? And then we have data after PCA, right, equal to PCA dot fit transform. And then we do the plot, right? Now, in the PCA, so we have to check the algorithm for PCA first to make sure that do we need the scaling, right? So let's go to here. So that is perform. So it used, okay, let me search it in the sklearn. Sklearn PCA. So it's gonna explain the algorithm. So use LabPIC implementation for full SVD and randomized SVD. And the method is from 2008, 2009. So if you look at the example, it should have example somewhere. Okay, so for user example, right? So you look at the example, it actually perform the PCA right away, right? You load in the data and then it perform PCA right away. So sometimes you don't need the scaling, right? I think it doesn't include scaling. Let me check the parameter when SVD server pack. Let me search the word scale. So the input data is center, but not a scale for each feature before applying. So in PCA here, it doesn't use, it use the SVD, singular value decomposition, right? So the input data is center, but not scale. So it means that in this library, the PCA does some kind of normalization for you, some kind of pre-processing. So we don't have to do the min-max scaler for this or standard scaler because the algorithm that we use, the library that we use have some sort of pre-processing included. So every time when you use a package, always go back and read the description, right? Because here I just show you that whenever you use library from outside source, you always have to read the entire document to understand which method it used and what are the exact steps that it try to compute. And if you know, then you don't have to do extra string. So you can, for this data set, right, you can just perform PCA right away. And let's see. So if we perform PCA, right, each color will correspond to each digit. And this is what we have after we map into two dimension. So you can kind of see group, right? They are group like the purple group, the dark purple group, maybe yellow and green on this side. But when you plot it like this, it actually doesn't see the separation, right? So your data have 10 class, but it's very messy. So let's try LDA, right? Let's try LDA because we can cheat because we have target, right? We have target, so we can try dimensionality reduction with the target. So okay, let me create another block code, right? So we want to now perform LCA, not LCA, LDA, like linear discrimination analysis on the data using target, right? So from scalar dot discriminant analysis, so they have the whole library for linear discriminant for LDA, right? So they have the entire library. So for PCA, right, it was part of decomposition, and there are many functions in the decomposition. But for discriminant, right, it actually have its own library. So the way that you set up is actually similar to PCA. Like you define the number of components, right? The number of components. We can actually look at the linear discriminant from here. It should be in discriminant analysis, right? And then this one only have linear and quadratic. So they actually have the quadratic version. So, but we're going to use the linear version, right? So the linear version, there are many parameters that you can try, right? The solver is basically pick the algorithm that you want to solve, right? So the one that I show in class, like the one that you have to solve the generalized eigenvector problem, is this method. Is the eigenvalue decomposition. But there are other methods like SVD and LSQR for doing the same thing, basically find the axis with the most class separation. And the default one would be SVD. I think it's a little bit faster compared to the other two, but you can try all of them. Like you can try all of them, and then see how it goes. So we're going to use the default one. Yeah, but I'm going to show I can show you that there are more than one method of solving. So I have the data. I transform the data into LDA, right? And then I can plot, right? I can plot the data, and let's see how LDA perform. So compared to PCA, LDA is actually a little bit slower. So if you compare, right, this is the PCA, like everything is in one big cluster. For LDA, right, the class, you can see more separation, right? Of course, you have 10 class, right? You cannot possibly project 10 class as a separate cluster clearly, but you can see that, you have yellow on one side, you have like purple, you have green. So compared to PCA, right? PCA, the green, the right green and then the yellow are actually on top of each other. But here you can see some separation, right? Some separation. So for LDA is good when you have category data, because the category data usually you cannot use it in the LCA, right? Because it doesn't make sense to reduce the dimension for this feature, the category data. But if you have category data, you can use the LDA, right? So for here, if you have many category data, you can try different feature as well, right? So for this, we have just, we know each group, right? We know each group, right? The group number 0, group number 1, group number 2. So we can use this group to perform the LDA. So how about the nonlinear? So maybe the fact that we didn't see a clear separation, maybe the data is nonlinear. The pattern is nonlinear. So we can try, right? We can try the nonlinear, right? So perform t-SNE on the data and plot. So t-SNE is from the manifold model, manifold module. In the manifold module is basically a graph made, a graph or like a geometric, and they will combine like the geometric distribution into this package, into manifold package. So we can say import t-SNE, and then you kind of do everything the same way. Oops. t-SNE, and then you can say t-SNE, and then you can specify the component, right? If you look at the manifold package, where is it? Manifold package. So in the manifold package, right? So they have more than one method, right? You have like multidimensional scaling, you have spectral embedding, is also another class of the embedding using graph Laplacian. So a lot of graph, a lot of the structure are in the manifold package. So in the t-SNE, as you can see, there are many parameters like perplexity is basically the sigma, right? So t-SNE, you compare the distribution of the original, right? The original you use Gaussian, right? The original use Gaussian, and the target you use t distribution. So the target t distribution, there's no parameter, but for the original graph, you have the sigma, which is basically the bandwidth, and they call it perplexity in this case, right? And the original is 30, right? So it's actually related to the number of nearest neighbor, right? So it's typically from 5 to 50. If you have a large data set, you might want to use 50. If you have small data set, you can use 5. For here, I'm not sure how many do I have. How many data do I have? Let me print number of data. So data.shape, okay. So I have about 20,000, right? About 20,000. So maybe I don't need a high perplexity. So I can say perplexity equal to 5. Let's try 5 first. Is the lowest we have. And then we can run the algorithm. So as you can see, it's a lot slower than LDA. So like PCA is the fastest. So it's the first thing that you always try. Because it's fast, you get the result quickly, and you know if it works or not. If it doesn't work, then you can move on to another method. But if it works, then you just stay with PCA. So this is going to take a little bit of time because it's nonlinear, and it actually compare basically every pair point. Even though we simplify the perplexity, but it still have to compare all pair. So while we wait for the t-SNE, let's look at how we can apply the UMAP, right? So perform UMAP on data and plot. Now, for UMAP, sklearn doesn't have a library or module for UMAP. So you have to find somewhere else. And luckily, we have UMAP. But for UMAP here, you have to you kind of have to install UMAP, right? So you have to install UMAP package, right? And then this package, right, if you search it up, right, UMAP learn, right? So it's a UMAP manifold approximation. If you go to like how to use, it's gonna tell you that you can use it at. Do you have the UMAP? No, right? Let's see. So yeah, import UMAP. All right. So you have to import UMAP. So you have to install it first because Colab doesn't have UMAP by default. So it's actually compatible with sklearn. Basically, you can use like 10-tail split. You can use everything from sklearn, but just the algorithm part, you just import from UMAP. So let's see. It doesn't include the instruction. So basically, you need to install the UMAP. And after you install the UMAP, you can use pip install and then UMAP. I'm not sure I need to learn. I think it should be learned as well. Do I have installation? So they actually do the MNIST dataset as well using UMAP. Basic UMAP parameter. So does it have? Oh, okay. So yeah, UMAP learn. So basically we are correct, right? So we install UMAP learn and then you can import UMAP. But the way that you use UMAP is actually the same, right? You call the UMAP model with the number of components can be 2. I think you can also specify the K, right? Let me check. Basic UMAP parameter. So you can pick K, I think, yeah. So you can pick the number of neighbor, like n neighbor, right? This parameter control how balance between local and global. So if you pick low value, right, it's gonna concentrate on the local structure. But if you increase the neighbor, then it's gonna use the global structure. So for n equal to 2, you have like the point that are close to each other in the local way. And then when you increase the neighbor, you can see the grouping, right? Right. So the point that are close to each other in the original space is going to come closer. So we can try maybe, I think, what is the default one? And neighbor, maybe 100. We can try 100. Oh, okay. So t-SNE. So as you can see, right, is actually, if you compare to LDA, right? So t-SNE is actually better in terms of separation. So you can see the purple class in one group, the green class is another group. And if we try UMAP, okay, let me install UMAP first. Can pip install UMAP. And then let's try n neighbor, right? N neighbor equal 100. And then let's see the result. So because we pick n to be the number of neighbor to be like very high, like 100 as this example, we kind of expect a similar result from the t-SNE. Right. So t-SNE we is actually project it such a way that the point are cluster in the original space, also cluster in the reduced space. And when you have this cup data in 2 dimensions, you can create a classification easier compared to this, right? Because you can see, you can actually like draw a line. You can draw a line to separate each group. So UMAP would be a little bit faster than t-SNE. So t-SNE take about 4 minutes to complete. So let's see how long UMAP will take. I think if you run on your machine, it might be slower than mine because I'm using Colab Pro. So I have more like processing power. So I guess it's a waiting. So yeah, so there are basically 4 methods of reduce dimension. And when you want to reduce dimensionality, it depends on what your application is. If you want to visualization, you have to try all 4 and then pick the best visual. But if you want to perform classification or something else, you still have to measure the performance in terms of accuracy. Like the model accuracy, if you want to use the classification, or if you do the regression, then you use like mean square error or map error score. Okay, so the UMAP, right, it actually do the grouping, but now there are more empty space, right? There are more empty space, and the group is actually like closer to each other, like compared to t-SNE, where the data is kind of spread, but they are like in the group. Here they are in the group as well, but they actually further apart, right? And usually only spend like 2 minutes, so it's like faster than t-SNE. Okay, so I will upload this file. Actually, like it's very easy to use. So yeah, you can just look at from the example code. I think they have example code as well. So you can look at this example. So next week, so hopefully, I will be able to hold the class on site. I will let you know. And next week we are going to start our first assignment. I'm going to create a Kaggle competition, and everyone can join the competition and do the homework on there, right? So you can create the notebook on the Kaggle website, and then you can run the code there, right? Yeah, I will upload this Python. Yeah, I will always upload the file that I do in class, so you can use as a practice. Any questions? All right. If there are no further questions, I will see you again next week. If you have not joined the class website, the Mango Canvas website, please be sure to join. I sent invite. I think some of you have not accepted the invite yet, so make sure that you do that, because I will post announcement like today. I post announcement, but I just remember that some of you are not in there, so I have to send email at night to remind that we will have the class online. So yeah, thank you all for coming, and I will see you again on next Sunday.